All right, boys and girls, welcome back to the drive-through. This Jacobian lesson is sponsored by the deli. Hungry? Stop by the deli and get yourself some 7-layer bean dip with some organic blue corn chips. Who would have thought there were blue corn? But there is. Also, I think we decided today in geometry that corn is a fruit and a vegetable. Is it not? What are you doing here? Okay. All right, so, Jacobian. A Jacobian is simply a factor. It's taking a region that is very complicated and it's turning it into a region that's not complicated. However, when you turn it into a not complicated region, you change the area. The Jacobian accounts for the change in the area. It's the best way I can explain it to you. So, the first way, we are going to write Jacobian as capital J. That's kind of ghetto, or jetto, if you will, but it's going to save us a lot of notational time, okay? The book, you will not see capital J in the book. The book writes it like this, okay? So that is their way of saying a determinant, but what the book leaves out is that the Jacobian factor needs to be positive. So in this case, that's an absolute value. What that means to you guys is that. Okay? That is indeed a determinant with an absolute value around it. That's why I tried to make the outside one bigger. Okay? And what that means, in case you've forgotten, is that. Top left times top right minus bottom left times bottom right. And we want it to be positive, so we stick the absolute value sign there. So far, so good? You don't know what we're doing yet, so it's totally fine for you to be confused. That is what the Jacobian is. Okay? So, okay, so let's say we've got some region, okay? And we've got some function of x comma y over that region, so some z equals. But let's say that our region is totally nasty, okay? However, we could express our x as some function of two other variables. And we could also express our y as a different function, but of the same two variables. I don't expect you to follow this yet, so just write it down and have open minds. If those are our circumstances, then we can change our region from an R to a different region, S. Okay? And now, instead of integrating over our function in terms of x and y, we're going to turn our x into the g of u comma v, and we're going to turn our y into an h of the same variables. Since we've changed the region that we're integrating over, we need to multiply by our Jacobian factor. And now we need to have it either in du dv or dv du. Okay. So now, let's see. We've got our change of variable formula. So now let's do this. Find the Jacobian for polars, for rectangular to polar transformations. Okay? So, how do we change from rectangular to polar? X equals R cosine of theta You didn't realize it at all. This is the exact situation that we're looking for. X is a function of two variables. Y is a different function of the same two variables. So the Jacobian is going to be, in this case, it'll be dx dr, dx d theta. Just remember, x is on top if you get confused, and then y is on bottom. Stay consistent. Since I chose dr on the left on top, then dr is on the left on the bottom, but I could have switched those because we're going to have an absolute value and it won't matter. So that's our Jacobian, right? So what is our dx dr? Now you got to get your mind switched back to integration. It's cosine theta and dx d theta negative r sine theta, dy dr sine theta, and dy d theta positive r cosine theta. Okay, so what do you get? You get r cosine squared theta minus a negative r sine squared theta, which equals what? Well, good. What was our factor when we changed from rectangular to polars? R dr d theta. Sweet. We just realized that we've been doing this already. We just didn't call it Jacobians. So what you've learned is that when you change from this polar sector to this rectangular region, the factor from here to here is r. Meaning this section is r times smaller than that one, okay? The height over the top of it hasn't changed because we've accounted for that by simply substituting for x and y. Okay? Stay with us. You're doing really, really good. Okay, so this will be the last question on the video, and it'll take us a long time, so stay with us. Here's what we're going. Now we've got a region bounded by these four lines, okay? So let me try to help you understand what you're doing by plotting these. We want to find this would be volume, right? We've got area times height, which is volume. We want to find the volume of the solid bounded by these four lines and this height. Okay? So, x minus 2y equals 0. What are my intercepts? Well, 0, 0, right? And then, what's another point on that? 6, 3. Is that right? Okay. And then the second one has the intercepts of negative 4, 0 and 2, 0. Or sorry, 0, 2. Okay. The next one is 4, 0 and 0, 4. Zero, 1 and 1, 0. Is that right? Okay, so here's what I want you to understand. I know I've already explained this to you, but for the video's sake, this is our region right here. If we wanted to use our current technique to integrate over that region, it is not vertically simple, it is not horizontally simple. We would have to let x equal this, and then x equal this, and then x equal this, and then x equal that. We'd have to have 3 different vertically simple regions to integrate over. So then we would have 3 double integrals, all of which had functions here and here. Okay? And it would be really nasty. So the whole point of this lesson is so that we don't have to do that. But what we're going to have to do is change this region. What shape am I coloring in here? That's a parallelogram. So we're going to have to change that, okay? Anyone have a suggestion? Well, let's try to make it a rectangle. If we can get it to be a square, great, okay? So let's let u equal what? X minus 2y. So then what are we going to say v is? Now look what that just did for us. Now, our u from this equation is going from -4 to 0. Do you see that? And what's our v doing? It's going from 1 to 4. So looking forward, these are going to be our bounds on our integrals. Because remember, when we switch from dx dy to what? To du dv. So that's a good thing. However, remember that x needs to be a function of u and v. Do we currently have that? We do not. So we need to take, I'm going to change colors here just to kind of indicate a change of thought. We need to take u equals x minus 2y and plug in what y is in terms of x and v. So what is y in terms of x and v? Y equals v minus x, right? Right? So now we're going to type it, we're going to put in, substitute v minus x. So u equals x minus 2v plus 2x. So 3x is u plus 2v. Do you agree? So x is equal to 1/3 u plus 2v. Now we have x as a function of u and v. So now what do we need to try next? We need to get y as a function of u and v. Well, y is v minus x. So y is v minus 1/3 u plus 2/3 v. Is that a plus? That should still be a plus. Did I do that right? Okay, and what's v minus 2/3 v? So y equals 1/3 v minus 1/3 u. So y is 1/3 times v minus u. Okay? Everybody following? Alright, so what comes next? Now we got to find our Jacobian. Alright? It is. But remember that you signed up for it, and 7 years ago we just would skip the hard stuff, and everyone was happy. So stay happy, but be happier that you're understanding more than other people once did, because that's what it's all about. Okay, so our Jacobian, are we good enough to partially differentiate without, no, I'm not going to do that. So let's write dx du here. So then what has to go here? Dx dv. What goes down here? Dy du. And here? Dy dv. Okay, so what's the derivative of x with respect to u? 1/3. What's the derivative of x with respect to v? 2/3. What's the derivative of y with respect to u? Negative 1/3. And the derivative of y with respect to v? Positive 1/3. So you get 1/9 minus a negative 2/9. So that's 3/9. So our Jacobian is 1/3. So here's what we did. Remember what our new rectangle was? What's u go from? U goes from negative 4. 1, 2, 3, 4. Oh, not blue. I can't write in blue. U goes from negative 4 to 0. Right? And what's v go from? V goes from 1 to 4. This is our region S in the UV plane. What do you notice about the pink shape? What shape is it? It's a rectangle. Sweet. Is it bigger or smaller than the black shape? It's 3 times bigger. That's why we multiplied it by 1/3. That's what we just figured out, just so you know. Okay? That's why our Jacobian is 1/3. This pink thing is 3 times bigger than that, so we need to make up for it by multiplying by some factor. Okay? All right. Here we go. So now we can transfer it. Here's what I did wrong in third bell. You guys are lucky. You get the next best version. We want to put anything with zeros on the inside. It makes the integration a lot easier. Okay, so what should we put on the inside then? U. What does U go from? Negative 4 to 0, right? And what does V go from? It goes from 1 to 4. It does not go to from 4 to 1. It's not how things are done in life. So get that out of your brain. Okay? Now we don't have a choice. So we've just chosen our integration order, and what is it? I literally forget. What was this one? This was U equals? And this is V equals? So it's du dv. Okay? Alright, so our original function was 3xy, right? So it's going to be 3, what's our x? 1/3 u plus 2v, right? And what was our y? 1/3 v plus u. Okay, that was from the 3xy was from our original problem. So let me scroll back up to the top, Sabrina. Remember this? Evaluate this region over this function. No problem. Got it? Okay, what have we not included yet? Our Jacobian. What is our Jacobian? 1/3. Yes. Thank you. Thank you. All right, we good? So now let's clean up all of our 3's and 1/3 and bring them to the outside, and then let's FOIL all in one step. So what are we going to have on the outside? 1/9 integral from 1 to 4, integral from negative 4 to 0. All right, so you get uv first outside minus u squared inside plus 2v squared, and last minus 2vu. All right, now this is bad teaching here, but I'm going to do it anyway. What's uv minus 2vu? Minus vu, right? So I just cleaned that up with my Interwrite pen. du dv. Okay? You with us? All right, now we've got to integrate that thing with respect to what? Okay, so that's a negative u cubed over 3 plus 2uv squared minus vu squared over 2, all from, whoops, negative 4 to 0, and we still have a dv left. Okay, so that's why it made it easier. We put in a 0 for u, and all that's gone. And then you do minus, so this is negative 4 cubed. So that's positive 64 over 3, right? Minus 8v squared, but aren't we going to actually subtract that again? Oh yeah, the 4 is being put in first. So that should be a minus. Everybody agree with that? No? It's positive because it was a minus.
Oh, I didn't say that. Wait, no, but you're subtracting a negative. No, it should be negative. Negative 4
No.
cubed comes out as a negative, and then you add the positive, so it's a negative. And then it's actually a negative. It's a negative. It's negative. Yeah.
Okay, remember what we're doing here. We're basically doing 0. When we put in a 0 for u, you get 0 for all those terms. And then you're getting minus this huge thing. When you put in a negative 4, you get a negative 64 over 3. Why is it 68? Okay, 64. But then when you do minus a negative, it becomes positive. No. Oh, yeah. Negative gets negative. This would be positive. And then you subtract it and it becomes negative. I'm with you now. I'm with you. This is why I'm filming in class. I tried to do this after school yesterday, and I kept getting the algebra wrong. It was so embarrassing. All right, plus. Well, we'll get back to the plus. Let's do this. So, put in a negative 4, square it. You get a positive 16. Put it in a negative 4. You get a negative 8v squared. So down here, plus 8v squared. Okay. Put in a negative 4 for u over here. You get a positive 16v over 2, but then it's a negative, so it's a minus 16v over 2, right? So it's going to be a positive 8v. And now we are going to integrate that with respect to v. That's one thing I like about calculus is that there's so much respect, you know? We're just respecting v right there. All right, 1/9 times negative 64v over 3 plus 8v cubed over 3 plus 8v squared over 2, which is 4v squared. Everything from 1 to 4, like this. Man, do I feel like pausing this and just letting you guys do this right now. All right, pop in the calculator.